Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on sequences and series. And one example here is, or one use case of using one of the sequence transformers to accelerate the convergence is that related to the perturbation theory. So I'm not going to actually talk about the details of perturbation theory in this lecture, but I'm going to talk about one of the use cases. And in general, the perturbation theory is about turning a hard problem into an infinite number of easy problems. And then basically we calculate the result of each of these easy problems and try to combine them together infinitely to find the solution to the hard problem. And what we usually do is we introduce a free parameter. So it's an extra degree of freedom. Some people just call it degree of freedom, a free parameter or another degree of freedom to the system. Typically we call that epsilon. And then we introduce it in the original problem, which is the hard problem, such that when we set it to 0, when we set this epsilon to 0, the problem is solvable. We can find the exact solution. The solution is known. And then we write the solution of the hard problem with the new degree of freedom, epsilon, in terms of a power series of epsilon. So we end up with a sequence or a series, right? A(n) epsilon to the n. And assuming an analytic behavior is that this series is more like a power series or a Taylor series. Remember, Taylor series converge for analytic functions, okay? So we assume that the solution to the hard problem is well behaved, which is not. In fact, most of the times it's not well behaved, but if it's not well behaved, it just means that this series is not representing an analytic function, which means that this series is in fact a divergent series. But that's not a major issue. We can resolve that somehow in most cases. So we do this, and remember the first term here, this summation starts from 0. So a0 epsilon to the 0th power. It's just a0, right? And a0 is basically evaluating this series at epsilon equals 0. So when we set the epsilon to 0, the solution is in fact a0, right? So a0. So we start by setting epsilon to 0 and find a0, and then we write the general solution like this series, and then eventually what we want is to set the epsilon to 1, because epsilon to 1 means we get exactly the hard problem. And the hopes here are that the radius of convergence of these power series is greater than 1, so that this becomes, when we set epsilon to 1, this becomes a convergent series, right? In most cases it is not, but let's not worry about that at the moment. And then once we have this series, and let's assume that it's in fact a convergent series, then we can use any of the accelerating methods or accelerating transformations. So if the coefficients turn out to be oscillatory, we apply Aitken or Shanks. If the coefficients are monotonic, we apply Richardson, and we can get a much faster approximation or acceleration for a convergent, right? So we don't need to calculate maybe 20-30 terms. Maybe we can just calculate the first 10 terms and then apply twice the Aitken transform or Shanks transform, and then we get a much more accurate result for the original series, right? Now, one example that is very interesting to look at is this case. Let's say we have this equation, x to the 5th power plus x equals 1. And we want to find the real root of this equation. Now, this can only have exactly one real root, because if you look at this polynomial and look at the derivative, it's 5x squared plus 1, 5x to the 4 plus 1. And it's strictly increasing, right? This means that if the function goes up, it never comes down. So this polynomial must have exactly one root. and we kind of can guess that the roots should be between 0 and 1, because if it's greater than 1, then x to the 5th is much greater than 1, and plus something greater than 1, it's just greater than 1, it's never equal to 1. If x is less than 0, then x is 0, negative, x to the 5th is also negative, therefore the whole left hand side is negative. So x, the root must be between 0 and 1, and this equation has exactly one root because of the strictly increasing behavior of the function. Now we have already discussed all of the common root finding methods, including bisection, trisection, Brent, Newton, Raphson, and other types of methods. Okay, secant, enhanced secant, false position. So we can use that. So let's try to do that first. So let's head to Eclipse. In our sequence, in the test package, let's create a class like test root finder, root perturbation. We want to have a main method. Let's call test1, and test1 is basically just using one of the root finding algorithm. Public static void test1. So let's we already have this roots project. In the roots project we have the real root function and then the real root. So I'm going to give a dependency, go to the build path, give a dependency to roots, and now I call the real root function. Let's call this func, which is equal to t goes to, or x for example, goes to x times x times x times x times x 5 times plus x minus 1. All right, minus 1. So we are getting x to the 5th plus x minus 1 equals 0. Okay, and then we have real root object. Let's call it root finder equals new real root. So we pass in our function. Okay, and then double result equals root finder dot bisection, and we already know that the root is between 0 and 1, and then sys out result. So this is the exact result, 0.75487766. So let's copy this, put it here as the exact value. So this is the exact value. Okay, now let's try to solve this and find the root using perturbation theory. So the perturbation theory says you introduce a new parameter epsilon in the system, in the equation. So I can put an epsilon here, epsilon times x to the 5th plus x equals 1, or introduce an epsilon here at x to the 5th plus epsilon x equals 1, and or introduce the epsilon here, so x to the 5th plus x equals epsilon, right? Now it turns out the best case here is the second one. So introduce the epsilon at x. So let's look at that case, x to the 5th plus epsilon x equals 1. All right, and then when we do that, so this is our general hard problem with the degree of freedom epsilon, and if I set epsilon to 1, I end up with this, right? So the solution to my hard problem happens when I set epsilon to 1. And then we write the general solution of this as a function of epsilon. So x of epsilon, which is going to be the root, is a summation from 0 to infinity of an epsilon to the n. Okay, now if I set epsilon to 0, x of 0 is basically a0. So a0 is the solution when I set epsilon to 0, and I already know the solution, and that's the whole point. When we set the epsilon to 0, the hard problem is supposed to become a simple problem or easy problem. So x to the fifth equals 1, so the solution is 1. So a0 is 1. And then what we do, we put this sequence series into the into this problem, and then find the coefficients in a recursive way, right? So a1 turns out to be minus 1 over 5. A2 turns out to be minus 1 over 25. A3 turns out to be minus 1 over 125. A4 turns out to be 0. And after that, the other coefficients become positive, and then 0, negative, 0, positive, etc. So A5 is 21 over 15, 625. A7 is 78, 78, 125. So as you can see, there is some sort of oscillation or alternating of the sign happens. But now what we want to do, we want to sum these up, right? A0 plus A, because when I set epsilon to 1, and it turns out that if you try to calculate the radius of convergence for this series, it's greater than 1. It's like 1.6 something. So setting epsilon to 1 causes basically gives us a converging sequence, so no problem there. All right, but let's try to actually numerically sum this sequence up and see what we get, and then try to, because the sign of the terms kind of alternate or oscillates, we apply Aitken or Shanks and see what happens then. All right, so let's go to Eclipse here. So in test 2, public static void test2, I'm going to create an array, let's say of double a equals so a0 is 1, a1 is minus 1 over 5, a2 is minus 1 over 25, a3 is minus 1 over 125, a4 is 0. And then A5 is 21 over 15, 625, 21 over 15, 625, and let's go back one more time. A6, it should be 78, 78, 125, 78 over 78, 125, all right? So I have A0, A1, A2, A3, A4, A5, A6, okay? Now let's try to sum this up. So let's create a sequence, just, and let's import it. Okay, we don't, so let's call this A sequence, okay? So basically n goes to series dot okay, we need to import it, and we also need to import series dot sum from okay, now we, in order to create the A sequence, n just returns an, all right? So I'm just returning the index of this array, and for the sequence, if you recall, we defined the variable as a long variable, so I just cast it to int because arrays are defined over int. And then let's call the partial sums a partial sum, and it's going to be a sequence. The partial sum is also a sequence, and basically n goes to series dot sum over a sequence. We're going to sum from 0 to n, all right? And then for int I equals 0, I less than a dot length, I plus plus, we're going to sys out a partial sum evaluate at I. So let's see what we get. Test 2, and maybe let's also do the exact here. All right, so the exact was 0.754877, and then we see that when we sum these terms for the sequence that came out of the perturbation analysis, the first is 1, 0.8, 0.76, 0.752, 752, 753344. So as you can see, we're definitely getting closer to the exact result, and we expect that because this sequence turns out to be a convergent sequence. It doesn't diverge, it converges, because the radius of convergence for the original perturbation series is greater than 1. And the last term is 7543, 7543, 424, and the exact result is 754877. So we get about 3 decimal places of accuracy. Now let's say we want to get a better approximation. How do we do that? And that's where the power of the sequence transformations come into play. In most physics problems, let's say you have a Schrödinger equation, you try to solve it using perturbation theory, okay? You are very lucky if you are able to calculate up to the 5th or 6th term, okay? Here we get 0, 1, 2, 3, 4, 5, 6, right? So you would be very lucky. So let's say we got lucky in this problem and we got these coefficients, but after the A6, the rest is, let's say we are just unable to calculate them. The question is, how much information does just these 6, 7 have? Can we just somehow extract a very accurate result just using these 6, 7 terms? And the answer is yeah. Let's try sequence transformations. Why not? And because of the alternation in the sign, we're going to use Aitken or Shanks. Let's try Aitken. So I'm going to create a new sequence. Let's call this BSEC, which is taking the A, and we're going to, you remember we applied this on the partial sum. So let's call this Aitken sum, Aitken partial sum. And we're going to get the A partial sum and call the Aitken on this, all right? And it returns a sequence. And remember, Aitken uses basically the nth term, n plus 1 and n plus 2. And now we have up to A6. So for Aitken, we can use, if I have A6, I can use Aitken 0, Aitken 1, Aitken 2, Aitken 3, Aitken 4, and Aitken 4 up to here, because for Aitken 4 uses A4, A5, and A6. So I cannot go beyond this because I don't have the rest of the terms. But now let's see what happens. So let's call this partial or A sequence. And then we're going to do Aitken partial sum. And obviously the length was 6. I have to go twice down that because Aitken uses at index n, it uses n, n plus 1, n plus 2. All right? All right, let's see what happens. Okay, the original A sequence turns out to be you see Aitken from the very start, from the very beginning, it's already 0.75, which is good because it's already 2 decimal places of accuracy, unlike the original sequence that started from 1, went to 0.8, went to 0.76, all right? But then it kind of stays there, doesn't add much, and then eventually it becomes 0.7572. So eventually it ends up with 2 decimal places of accuracy, whereas the A sequence, it has at least 3 decimal places of accuracy. Let's try now let's try to go with Shanks. So Shanks partial sum, A partial sum, we're going to Shanks it, and then Shanks partial sum. And but remember, for Shanks we have to start from 1 because at n it uses so let's write the comment here. For Shanks, it uses n minus 1, n, and n plus 1. So if I have A0 to A6, I can have S1, S2, S3, S4, and S5. Okay, so I can go from 1 to so the length of A is 7. Actually, I think we could for 8can we could go higher, so let's try it again. No, we end up with an array index out of bound. Okay, so for Shanks, we still end up with the same thing as 8can, so there is not much difference between Shanks and 8can. But let's try to do 8can again. So we try a new sequence 8can2, and we get 8can partial sum and 8can it again. Now we have basically what are the indexes? Now we can go to 3, right? Because A0 uses 0, 1, 2, A1 uses A1, 2, 3, and A2 uses A2, 3, 4. So we can go to 2, and let's see what happens here. So we are using the second order 8can, so or applying 8can twice, 8can2 or 8can 8can2. Array index out of bound. Okay, so we should go to 4, I believe. Five or 3. No, so we should go to 4. So the original sequence is like this. 8can sequence is this, and then the second 8can is something like this, 7, 5, 2, and we have 7, 5, 48. So as you can see, we're pretty close. Not as close as the original sequence, but still just by applying 8can one time we get 0.75. And you probably can see that the problem here is that there is a 0 here, and that 0 causes the 8 can. So but what happens if we use Richardson? So let's try Richardson. So we do Richardson, we get a partial sum, and then call, let's say, Richardson. And Richardson uses n plus 1, an plus 1. So Richardson, the first order Richardson uses n and n plus 1. So we go to a dot length minus 1. Richardson partial sum, evaluate. Okay, so Richardson starts from 0.8 and then 0.72, and let me see if I can put this here, for example. Let's minimize this, and also minimize this. All right. So Richardson starts from 0.8, 0.72, 0.736, 0.752 basically, 0.7587, 0.7593. So it kind of gets away from the exact solution, which is 0.7548. So it just seems to increase more and more. But 8can and 8can2, they remain around 752. Okay. And what you can see, it's what is very interesting here is that the first three terms of the sequence are 1, 0.8, 0.76, which has a relatively large error, right? But then the first 8can is about 0.75, which is much closer. And if I just use 4 terms of the sequence, I still end up with 0.75. Okay. So this shows that we can in fact use perturbation theory and combine it with the power of sequence transformation to be able to accelerate the result of the perturbation theory. And again, understanding sequences and series are very interesting and very important. So I hope you enjoyed this lecture, and stay tuned because I will have more lectures coming soon. And thank you for watching, and I'll see you in the next one.